Problem number 12 in the test 2 review tells us that we have an open box with a volume of 98 cubic inches, and we want to figure out the dimensions of the box using a minimum amount of material. So we're trying to minimize the amount of material, but we know what the volume of the box is. So let's draw a picture of a box to start with. I like to draw pictures when possible. So we have here an open box, which means it has no top on it. So the box is going to look something like that. And we know that the base of the box is a square. So that means we would call the length and the width of the base by the same letter. I'm going to call that x. So the base of the box is x by x. And then the height of the box I'm going to call h. So what we know about this relationship between the h and the x, we know the volume of the box is 98 cubic inches. So that means that h times x squared has to be equal to 98, because the volume of a rectangular box is length times width times height. So that would be x times h, and I'm choosing to write that as h times x squared, which then means that h is equal to 98 times x to the negative 2, or divided by x squared, whichever way you want to write that. So now the amount of material that's being used here is basically the area of the 5 sides. Remember that the top, there is no top on it. This is just an open box. So the amount of material, we have 4 sides, which are rectangles, and the area of each one of those rectangles is h times x. And we have 4 of those. So those are the 4 sides of the rectangular box here. And then we have one base, and the area of that base is x squared. So 4hx plus x squared is the amount of material that's being used. So this is our function, but this function has 2 variables in it. But we have a relationship given between those 2 variables. We know that h is equal to 98 over x squared. So if I replace h here with 98 over x squared, we would have just the one variable. So m of x will be equal to 4 times 98 over x squared times x plus x squared. And that is our function that represents the amount of material used to make this box. So the next step is to clean up this algebra a bit. So cleaning it up, we would get 392 x to a negative 1, and that's just one of the rules of exponents. This is x to a first power, and then on the bottom we have x to a second power, and since 1 minus 2 is negative 1, we know that reduces down to x to a negative 1, and then that's plus x squared. And now, once we've got that algebra cleaned up a bit, we want to take the derivative of this function. So the derivative here, m prime of x, is negative 392 x to negative 2 plus 2x. So now we want to set this equal to 0 and solve for x. So setting that equal to 0, and I could rewrite this algebra a bit. I'm going to make this a little bit smaller, so I have a little extra room here. Whoops. So this we could add 392 over x squared to both sides. So that's equal to 392 over x squared. And again, all I did was add 392 over x squared to both sides of that equation. And if we multiply both sides by x squared, we would get 2x cubed equals 392. So x cubed would be equal to 196. And then if we take the cube root of both sides, just use your calculator to take the cube root of both sides, we get x equals, and I believe it asked for 2 decimal places, so that would be 5.81 if we round that to 2 decimal places. The calculator actually gives 5.808785734, which I would keep that number in my calculator in order to figure out the h. So h, we know, back up here, we know that h is equal to 98 divided by x squared. So if I do 98 divided by that number in the calculator squared, I'm going to write down just 5.81, but I'm actually going to use the number that's still in my calculator. So 98 divided by, and on this particular calculator, the one that I recommended, you can pull that answer back up by saying second answer and then square it, press equals, and that gives me 2.90. And that is going to be the dimensions of this box. Now, if we wanted to verify that this is truly a minimum and not a maximum amount of material, we could test this 5.81 on a number line. So if I put 5.81 there and plug into the derivative, and I verify that the graph is decreasing before that point and increasing after, that way I know that's a minimum rather than a maximum, because finding a minimum and a maximum, it's the same process. Take the derivative, set it equal to 0, solve for your independent variable. So in order to verify, like if we had 2 answers to this problem, we would need to know which one is a minimum and maybe the other one's a maximum. But on this one, since there was only one answer, you can trust the book that they're asking you for something that exists. So I hope that helps. Sorry, I got a little sloppy there.